A very good morning to all of you. Today we are going to discuss heuristic search techniques. We have already seen uninformed search techniques in the previous session. So now we are moving to heuristic search techniques. And we will discuss generate and test and hill climbing method in this session. So we will see informed search strategies or heuristic search strategies. So we begin with a real world problem. So if we are using Google Maps to go from hostel to railway station. So whether we will randomly try all the notes? No, right? So we should have some information about the routes. So it uses, in the case of informed search strategies, that uses domain-specific hints about the location of goals and can find solutions more effectively than an uninformed search strategy. So we have already seen uninformed search strategies, for example, BFS and DFS, that explores blindly. So in real systems use knowledge about the goal location to guide the search. So heuristics actually helps the algorithm to guess which direction looks promising. So informed search uses domain specific hints. So these hints are encoded as heuristic function. So we can see here it is h of n. So h of n is equal to the estimate cost of the cheapest path from node n to the goal state. From node n to the goal state. H of n means from node n to the goal state. What is the estimated cost of the cheapest path? And here we can say that it is not exact, but it is the best guess. And it also depends on the problem knowledge. H of n does not tell how we reach n, only how far n is from the goal state. So we can, for example, we can say that if we are considering a city, uh, we can consider each city as a node. And for example, we can say that if we want to travel from Kerala to Hyderabad, so here this is the direct path, or we can say that these are the roads. So there is a actual road distance is there. So this is Kerala and this is Hyderabad. And if you want to travel from Kerala and Kerala to Hyderabad, we are choosing this road. And that is a real distance that we can consider as a real cost. And but there is a straight line distance is there, and this is the straight line distance. SLD, we can call it as SLD, that is the straight line distance. So this straight line distance is the heuristic. So there may have the actual distance may be 630. We can say we can just take it as this is 630 kilometer, but the straight distance may be less than that. It may be 515 kilometers. So this straight line distance we can consider it as heuristics. So in h of n is the straight line distance to goal. And it is actually easy when we are using this straight line distance, it is easy to compute and also never overestimates, and also it will be closely related to the real cost. And we have already seen uninformed search techniques in the previous week, and there we have to expand all the nodes in all directions, and there is a large search space, and also it will take more time, and we need a high memory cost. But in the case of informed search techniques, it expands nodes closer to the goal first, and also it will prune the irrelevant parts. And it is not needed. It will prune it, and it is more faster convergence. So we can say that heuristic reduce the effective branching factor. Now we are going to discuss the generate and test heuristic search. So for example, we can say that if we forgot our phone somewhere in our house, our way is to check every room, every table, every drawer until we find it. So this is an example of a generate and test. So we first generate a guess, check one place and test it if the phone is there, and repeat until we found it. So here Generate and test is one of the simplest problem solving strategy in AI. First, the algorithm generates possible solutions. Then it tests each solution to see if it meets the goal state. It keeps going doing the same thing until the best or correct solution is found. So the solution must be complete before testing, and the partial solutions are not tested. So here it is, we are specifying it as all possible solutions. So that means this is actually an exhaustive search. Generative and test tries every possible solutions and guarantees finding a solution. But it will be very slow for a large problems. And here we can say that it uses brute force algorithm. And one example it is mentioned that British Museum algorithm. So they are actually this is finding a book in British Museum by walking randomly and hopping. We bump into it. So this is a random generation of solution, and there is no guidance and there is no guarantee about the success, and they used mainly as a conceptual explanation. And it is mentioned that DFS with backtracking. So that means when a generate test is done systematically, it looks exactly like DFS with backtracking. So DFS we already discussed in the previous classes. That is DFS generates one full solution path. If it fails, it backtracks. Try and next possibility. So example, NQ problem, Sudoku, puzzle solving, and the same algorithm we can apply there also. And we will see the algorithm. Generate a possible solution for some problem. This means generating a particular point in the problem space. For others, it means generating a path from a start state. So, for example, we can say that if we are considering a board configuration in NQ problem. So, NQ problem we can start it from a particular point in the problem space. There is we can say that we can start from a particular point in the problem space. But for example, if you are considering a route from city A to city B, then we can generate a path from the start state. So we are not guessing partially, the solution must be complete. And next step is actually test the solution. Now we test whether the solution is acceptable, and we have to compare with the goal state and check the constraints and also use heuristics or evaluation function. We have to check, for example, in the case of Sudoku, we have to check whether is the Sudoku valid for an NQ problem. Do the Q attack each other for finding a path? Does the path reach the goal state? Then next step is stop or repeat. That means if the solution works, we stop, otherwise we try again. Success means we will terminate and failure means generate another solution. So generate and test is a simple but it is inefficient. Without heuristic, it is blind. So with the heuristics, we can say that it is BFS backtracking and it becomes practical for small problems. Next, we can see hill climbing algorithm, that is an informed search technique. Imagine if we are blindfolded and standing on a hill, and you can only feel the ground around you, and each step you move in the direction that goes up. So here we can say that you don't see the entire hill, and you only know your current position and nearby position. So hill climbing, it is similar to climbing a hill. At each step, it moves to the neighboring state with the highest value for maximization case and for lowest cost for minimization. We will discuss in detail. So we can say that hill climbing is a local search algorithm. So that means it focuses only on the current state. There is no full path is stored, only one state is maintained in memory, and it is suitable for optimization problem. Optimization means finding the best possible solution among many possible solutions. So we are not just finding any solution, we want to find the best solution according to the some measures. So that measures may be the value that may be maximized, or we can say that the cost that should be minimized. So we will see in some problem higher is better. So we can call this as maximization. That means, for example, we can say that profit in a business, accuracy in a machine learning model, or a height while climbing a hill. And here each state has a value and goal is to move forward to or towards the highest value. Now hill climbing moves towards the neighbor with the highest value. And then minimization problem means in some problem, lower is better. We can call it as minimization. For example, we can say that distance travel, time taken, energy consumption and all, where each state has an associated cost and the goal is to move towards the lowest value. Hill climbing move towards the neighbor with the lowest cost. And next point is hill climbing is greedy approach. That means it chooses the best immediate neighbor, does not consider the long-term consequences. And next point, no backtracking. So that means once hill climbing moved forward, it never come back. That means no memory of previous states. We will not store any previous states, and it will save time and memory. And but there is some risk for getting it may get stuck in some cases, and we will see in detail. So that means in hill climbing, what it will do is it will evaluate initially, it will evaluate the neighbors and move to a better one and it will be repeated. And then when it will be stopped means stop when no neighbor is better. So we can say that hill climbing is greedy, local and iterative optimization algorithm with a no backtracking that stops at a local minimum. So we will discuss what is local minimum and all in detail. We will see the features of the hill climbing algorithm. So hill climbing work exactly like climbing a mountain. We are actually always move upward and step by step, and you cannot go any higher, and then we will stop it. So here we are considering the height as the value, and peak is the will be the best solution, and neighbors will be next possible move. So we are discussed all these points. Anyway, we will discuss once again. We will just go through it. Hill climbing is a local search because it only looked at neighboring points, not the entire mountain. So the algorithm stops when it reaches a point where there is no neighboring state as the highest value. So this actually, if we are considering a mountain, we are hill climbing and actually search for a next highest value. So it may be a local peak. It may not be the global peak. This is the global peak, the highest solution. So sometimes if we are searching the neighbors and we are selecting the next position means we may choose the local peak. It may not be the global peak. And we have seen the hill climbing is mainly used for optimization problem. For example, in the case of traveling salesman problem, we can consider each city as a states and total distance is the cost. And their goal is actually we have to minimize the distance. So lower distance will be the better value. So the algorithm it will swap the cities and keep the route with the shorter distance. So hill climbing always improves the solution gradually. And the next point is actually hill climbing is greedy because it chooses the best immediate neighbor. It actually does not check further possibilities. It does not compare multiple paths. And so, for example, we can say that here the current node, it is 10 and it has three neighbors. And first one is 8 and next cost is actually 12 and then 9. Then it will actually choose. First, it will check with the 8, so it is lowering, cost is lowering. Next is actually you can see it is 12, so it is increasing, so it will select this node 12. So it will move directly, move immediately to 12. So here we can say that state is actually the current solution and value will be the quality of the solution, how whether it is a best or not. So each node in the hill climbing has only two things, the current state and how good it is. And in the case of traveling salesman problem, each cities is a state and the total distance is the value. Or according to the value, we will decide whether it is a good or bad decision. So we can say that hill climbing works well only when a good heuristics is available. So heuristic means evaluation function. It guides the algorithm towards the improvement. So poor heuristic means that will result in poor result. So, and also we can say that hill climbing is memory efficient. There is no search tree, no graph storage, no memory storage. We can reduce it, and only one current state is stored. That is why hill climbing is fast, but it is risky. We will see one example of hill climbing, that is simple hill climbing. So simple hill climbing is the most basic form of hill climbing. It will move to a better neighbor, and the difference is how the neighbor is chosen, how we are choosing the neighbor. We will see actually there here we have a current node, and we have multiple neighbors are there. So then in simple hill climbing, neighbors are checked one at a time, not all at once. So that means there is an order of checking neighbors. Algorithm does not compare all neighbors. So there is an order. So according to the order only, it will. So if it finds a neighbor that improves the cost, then it instantly chooses it and moves there. So we can say that it stops checking as soon as it finds a better neighbor. So it is less consuming, time consuming, and the less optimal solution, and the solution is not guaranteed because here it is 10 means here it may be 8 and it may be 12 and it may be 15, and if the order is like this, it will first check this node and then check this one. There is an improvement and it will choose it here, but this is not the best solution. Actually here 15 is there is a large improvement is there, but here first improvement itself we are selecting this. So it does not guarantee the optimal solution, but and it is less time consuming. And we can say that here, even though 15 is better, the algorithm moves to 12 because it is the first improvement. So that is why it is called a greedy and short-sighted actually, because simple hill climbing is fast because it does not evaluate all the neighbors. It is actually less time consuming, and also because it stops the first improvement, it may miss a much better solution. If no neighbor improves the cost, then algorithm stops, and even if a better solution exists elsewhere. We will see the algorithm. Hill climbing improves a solution step by step using a heuristic value. These steps describes how the algorithm always run. And here we will see first the algorithm start with an initial solution. It will evaluate using a heuristic or evaluation function. Then if it already satisfies the goal, then it will stop immediately. And for in the case of TSP, the initial route if that is the destination city, and then it will stop it. So hill climbing may succeed immediately if we start at good position. Then we will see we have a loop until a solution is found and there is no new operator left to apply. So that means now the algorithm enters a loop and it keeps running until a goal is found or a no better move is possible. So an operator is an action that generates a neighboring state. So we can say that in the case of TSP, that is traveling salesman model, swapping two cities, that is an operation or action. We have already discussed that. Then next is actually select and apply the operator. That means next the algorithm applies one operator to move to the neighboring state, generate a new child solution or a new next move, and only one move is considered at a time. So hill climbing does not generate all the neighbors at once. Then next step is evaluate the new state, break this actually we can see three states we can see here. If the new state satisfies the goal, then algorithm stops. Then next case, if the new state is better than the current node, we accept it. So then new states, that means it will accept it and new state will be the current state. And better means we are actually, we will check the highest value or the lowest value depending upon maximization or minimization. Then next point is if there is no better than the current state, then return to step 2. That means we are entering into the that loop we will continue. So these are the three cases we have. Then whenever we find a solution, we will stop it, or there will be no better solution or no further moves, then we will stop it. That is, we are examining the neighbors, and if there is no further betterment, then we will stop it. Next is steepest ascent hill climbing. So steepest-ascent hill climbing is an improvement version of simple hill climbing. So both are greedy local search algorithms. Both move to a better neighbor, but difference is how neighbors are selected. So in this case, if we have we can consider the example. We have current node is 10, and we have three neighbors 12, 15 and 11 are the neighbors. So here, unlike simple hill climbing, which picks the first better neighbor, steepest ascent checks all neighboring states. So compare all neighbors and choose the one with the highest improvement towards the goal. So that is why this is called the steepest ascent. So it finds the steepest slope. So here it will check 12, 15 and 11 and it will choose the best improvement, that is 50. So in the case of simple hill climbing, it moves to the first improvement, maybe the 12, but here it moves to 50. So by looking all the neighbors, steepest ascent is more likely to find a better solution than simple hill climbing. And here it is a less chance of getting stuck in a small local peak and it will move towards steepest improvement. So because it examines all the neighbors, it consumes more time and computation resources. So here we have more comparisons will be there, and when compared to simple hill climbing, it is slower. But here we can say that it may take more time and computer research also needed more, but this is it will give a better solution. So, for example, we can say that we are climbing a mountain blindfolded. Then simple hill climbing move in the first direction that goes up. But in the case of steepened ascent, it checks all the direction and choose the one that goes up the most. So we can say that steepest ascent hill climbing evaluates all the neighbors and move to the one with the highest improvement, making it more accurate but slower than the simple hill climbing. We will see the algorithm. Step 1 is evaluate the initial state. That means start with the initial state, evaluate it using the heuristic. If it is already the goal, then we will stop it. Otherwise, we are making it as the current state. So in this case, actually, we will always start by evaluating the initial position. Then we are entering into a loop, and the algorithm now loops until either a solution is found or the current state cannot be improved. So here we can say that no better neighbor, then there will be no better neighbor means then it will exit, otherwise it will continue improving. So climbing a hill, unlike you reach the highest nearby peak. So here we are initializing a variable that is success SUCC, and at the it is a this is temporary best neighbor found so far in the current iteration. So at the start of the each loop, success for the best candidate neighbor. and it will compare all the neighbors before deciding which way to go. Next, examine each neighbor, therefore each operator that applies to the current state and generate a new neighbor and evaluate it. That means we are applying an operator and generate a new state and evaluate the new state and we will compute the heuristic or cost and compare it with the current state, that is success. And if it is better, then we will update the success. Otherwise, we will stick on that itself. That means, for example, we can say that we are in the previous slide we have discussed the current state is 10. So, success will be 10 initially. Then we have 3 knots and there we have seen the improvement 15. Then next success will be 15. So after checking all the neighbors, compare success with the current value. If success is better, move to the success. So current state will be is equal to the new best neighbor. So algorithm iteratively move towards the steepest ascent. And then the algorithm exit when no neighbor is better than the current state. That means we reached the local maximum. It can be global maximum if the heuristics is perfect. And if there is no further improvement is possible, then we will exit. So we can say that in the case of simple hill climbing, it will pick first better neighbor, but in the case of steepest ascent, it will look all the neighbors and pick the best one. So steepest ascent hill climbing evaluates all the neighbors and choose the best and move to it and repeat until no better neighbor exists. Next, we will see stochastic hill climbing. Stochastic hill climbing is variant of hill climbing where we don't examine all the neighbors. Instead, we pick neighbors at random and decide whether to move based on the improvement. So, unlike steepest ascent, which picks the best neighbor, that means stochastic hill climbing introduces actually the randomness into the search. So, it is useful when too many neighbors are exist and the search space is large. So at each step, the algorithm randomly select one neighbor of the current state and instead of evaluating all the neighbors. For example, we can say that if our current state is 10 and we have 3 neighbors, here we have 11, 15 and 12. So here it picks randomly. So neighbor picks randomly and we are picking 12. So decide if moving to 12 is beneficial or not. So that means random sense actually reduces computation. It makes less predictable than steepest ascent. But here once the neighbor is selected, algorithm decide where to move based on how much it improves the current path. So if the improvement is large, then highest probability of moving. And improvement is less, then there is a lower probability. So sometimes it may skip a neighbor even if it is better. So that means imagine we are climbing a hill, but sometimes taking smaller or less steep that steps to explore the areas. So we can say that it evaluates neighbors randomly and it selects a random neighbor and that improves the current state. And there is a probability of choosing a neighbor depends on the improvement and it do not always pick the steepest move. So this randomness can help escape local maxima that simple or steepest ascent hill climbing might get stuck. So we can see that here steepest algorithm anyway steepest ascent algorithm anyway it will provide the best solution. Here it will randomly choose the neighbor and then whether it will be going or explore the node it will be depending upon the probability. That means depending upon there is a large improvement or lower improvement. So accordingly, according to the probability only, it will select that particular. Thank you.